first speaker this morning is Professor Thomas Schick from Göttingen, and he has made a lot of contribution to topology and theory of index theory of elliptic operators. And I heard his name on several occasions. And when I was asked to nominate some speaker here, I thought that I could take advantage of this opportunity to invite Professor Schick to Kyoto. And he kindly agreed. And so I'm very happy to introduce Professor Schick again. And he's telling us topology of positive scalar curvature.
Yeah, thank you very much. Thank you for the invitation here. It's not my first time in Kyoto. I was here as a tourist on the occasion of a conference visit in Nagoya. But it's the first time that I'm here at the very famous RIMS and University of Kyoto. I'm really grateful to be at such a prestigious place. It's actually good for my voice. Here, but I'm a bit. Okay, very good. Right, so let's get started with the math. And I want to describe you one of the geometric questions to which is index theory, which was just mentioned, is applied. So a question at large would be, if you're given a smooth manifold, M, and let's say to fix the ideas, it should be compact and should have no boundary. What are the possible Riemannian, let's say, geometries on M? Okay, so let's draw a picture. So M could be the only manifolds we can really draw are two-dimensional manifold like a sphere or like a torus, right? And if I draw them like that, I embed them into R3 and they come kind of automatically with an induced Riemannian metric. And you can see that we can, of course, also make it differently. So we could have a bend here, which creates such a saddle situation here. But then we could also care about the question, can we put such a saddle-like situation everywhere on the two-sphere, right? This kind of question is the question I'm addressing here. And inspired, well, maybe inspired by this be just a bit more specific. Can we find metrics such that the scalar curvature function is everywhere positive? Nothing in a second. Why this particular question is particularly interesting. Okay, so that's kind of making this general question, which is very vague, slightly more specific. Right now we have a very concrete question to answer, and before we can answer it, we should understand a little bit about this scalar curvature. That is, given the Riemannian metric, a smooth function on the manifold with values in R, and we should try to understand what this means, right? Is given as follows. So in the 2D case, which is the case where we can draw the pictures, I'm just describing the three pictures which describe the difference between positive and negative, and intermediately we have, of course, 0. So how does a flat two-dimensional manifold look like? Now, can you perhaps help, Manfred? Flat, okay. If it's equal to 0, it's hard to draw because it's already there, right? That's the flat case. Now, you should continue to help out. So how does it look like if it's positively curved? Right, this is the model case of the sphere drawing there. So the typical point, that would be the point x. Typical point where positive curvature is just any point on our standard round sphere. And of course, if you want to make the curvature bigger, you have to make the sphere smaller. So then the curvature is bigger. And the negative case, I've also drawn already. This is exactly this saddle situation. And so if x is like that, then you have the negative curvature. Now, how about the higher dimensional case? Again, that's in some sense not difficult to understand, with the one exception that we don't really understand because we can't see these higher dimensional metrics. But the high dimensional manifold, if you pick a point, you can look at all the surfaces inside, all the two-dimensional surfaces going through that point, and you just average the curvatures, which are defined like that, over all possible curves. So that's, of course, not a precise definition, is the average of all scalar curvatures of the surfaces through that point. And you can make this precise in many different ways. You write down the curvature tensor and you contract it twice, or you averaging, of course, means you integrate something. But I could also give you a quick and dirty ad hoc definition, which is really a certain proposition that this definition gives rise to that. And again, this is something we can see here. So if you have a Riemannian metric, we know it's good for many things. In particular, it's good for measuring distances, right? The distance between 2 points is given by the shortest curve between those, the length of the shortest curve. And so if you have a point x in our manifold, we can use this distance concept to define the ball of radius r around x in the manifold, all points of distance less or equal to r. And the second thing we can do if we have a Riemannian metric is we can measure volumes. The Riemannian metric gives us a volume form. And so we could use the metric again to look at the volume of this ball. And, well, you can compare this to the volume of this model situation, which would be the flat case. So we take a Euclidean ball of radius r inside Euclidean space of the right dimension, n is the dimension of the manifold, and we can make this comparison. And of course, if we zoom in, if you look at small scales, the two things will be pretty much the same. So, but they won't be quite the same. So if you do a Taylor expansion, we get some non-trivial further terms. The next term which shows up is the quadratic term, and it turns out that this is exactly given up to some constant, which depends on dimension, which is non-zero, by the scalar curvature at the point x. So this Cn is strictly positive. And then there are higher order terms. And if you want to, you check it here. By the co-area formula, the volume of a ball of radius r, because the circles of radius r are shorter than Euclidean space, will be smaller than you expect it to be in Euclidean space, whereas in the saddle situation will be bigger. Okay, and that's exactly what you see here. Why did I write this down? It's not particularly suitable to compute anything, but it should tell you that this is really a rather weak invariant, the scalar curvature. It doesn't measure much. It just measures the expansion, the volume expansion of small balls. And nonetheless, I'm asking the question, are there global consequences this positivity of the scalar curvature would have? Right? So in dimension 2, you might expect global consequences because there the curvature is just, it's only the two-dimensional part we see. But in dimension 27, you might be more surprised if there are any global consequences because of this weak properties. So now, so the surprising answer then might be some kind of answer. Indeed, there are obstructions to the existence of positive scalar curvature metrics on M. And let me tell you how the structure of such obstructions looks like. Structure or model case would again be the two-dimensional situation. So we're back to situation up there. And what we need some magic relation between the geometry, where the scalar curvature is our input, and the other thing is just the pure topological type of the surface. Yeah? So now we could another quiz and test. So Manfred is my picking out person today. You have an idea what would be in 2D a good way to connect geometry and topology here?
Something like John Wayne theory?
Yeah, the baby version of it maybe. We go back quite a few years. We go to my former colleague, who passed away unfortunately, Carl Friedrich Gauss. And well, I think the more precise version is formulated by Bonnet. And what does the Gauss-Bonnet theorem tell us? It tells us that it's exactly this. It's the connection between geometry and topology. It tells us that something purely topological, the Euler characteristic of the surface at hand. Of course, we know that this is the only invariant we have to care about. That this can be computed purely geometrically for such a smooth, closed surface in terms of, gosh, now I didn't prepare the constants. So there is some, I think it's 2 pi, but don't take this completely granted. This times the integral over the scalar curvature for whatever metric you pick on the surface, and you also use the volume form, over the surface. So the integral over the scalar curvature gives you the Euler characteristic. And here you see the geometry is here. And it's very clearly related, because there's an equal sign, to the topology we see here. And what's the consequence? Positive scalar curvature is only possible if you take the connected ones, the connected surfaces on the two-sphere and on the real projective plane. Because these are the only surfaces which have a positive Euler characteristic, and an integral of some positive function will give you something positive. So, and of course, I'm also using this classification of surfaces along the line. So, we want to go to higher dimensions. Things are going to be more complicated. So one of the things you might hope to get is something like that, where the Euler characteristic formula for higher dimensions, which exists, is involved. But unfortunately, that's not really working because the curvature term in higher dimensions for the Euler characteristic is just something completely different. It's not depending so much on the scalar curvature, it depends on other things. And we might look at the following example. Take any M, so just a closed smooth manifold, and let's take one which has almost the same Euler characteristic, namely take the product with S2. Or actually, we could take any sphere of dimension bigger than 2. My claim is that this always has positive scalar curvature, and the trick is simply we can take the product metric. We'll take just an arbitrary metric on here. You take the round metric on the 2-sphere. But then you scale the standard metric on the 2-sphere. Okay, now if you make it tiny, we make the scalar curvature really big. And in our averaging procedure, eventually the directions of the sphere with some dimension-dependent constants. Yeah. I don't know precisely which, but if you look at the contraction formula, you see it's giving you a number of directions in the 2 factors also play a role. So you see there's some subtlety, because there are some manifolds of very simple type which are just always there and have positive scalar curvature. That's again maybe just to increase the suspense why there should be instructions at all. Right. And I was planning to, so now the higher dimensional instructions to positive scalar curvature exist based on index theory of the Dirac operator. And that's going to be a quite long story. And I want to give you one of the more recent and finer sample results. Which I hope to get to how the proof goes toward the end. Which is the following theorem, which in some special version goes back to Gromov and Lawson. And this general formulation is due to Bernhard Hanke, Daniel Pape, myself. So this is a jump now. I'm just giving you a sample theorem of the kind which works, and you will see much easier ones just a little bit later. So the situation is the following. If M, as above, so compact, no boundary, now I have to add a couple of conditions. So this annoying S2 there, we should somehow avoid, right? I mean, the conclusion will be when M has no metric with positive scalar curvature everywhere. So we have to avoid this S2. And one way to do that is to say there is no 2-sphere homotopically non-trivial inside M at all. So let's also assume it's connected. So this just means every 2-sphere you map into it can be deformed to a constant map to a point. And that's not possible with M times S2. So then I need something I have to talk about a little bit later, I need that M is a spin manifold, has a spin structure. If you haven't seen that, this is like having an orientation, but square, this condition. So it's quite a bit harder, but it's satisfied it in many interesting examples. And this is a standard condition we have to impose. Now I want that inside M, there should be a codimension 2 hypersurface. So the difference of dimensions is 2, such that, so this has to satisfy two things. N has a trivial normal bundle, which means we can actually thicken this embedding. So we find
Isn't the spin condition a consequence of the dimension of the second homotopy group?
not if pi, the first homotopy group, is possibly non-trivial. But you're close to it. The universal covering of this thing will always have a spin structure. So I want actually a fattening of this embedding to an embedding of n times a 2 disk. So it just means we have a trivial normal bundle of this codimension 2 hypersurface. And I want that on the level of fundamental groups, pi1 of n also injects, induced by this inclusion map, into pi1 of m. So actually this is automatically in what comes next, implying that this inclusion will have infinite index. So infinite index situation here. And finally what I need is that something I call the index of n, or of the spin structure of n, which is automatically given here, should be non-zero. And now this is what I have to explain later again. This is going to be an element in an interesting and complicated group in the K-theory of the reduced C-star algebra, of the C-star algebra of the fundamental group of n. Okay, so what is the structure here? Just to compare it to what I sold before. This is something, in some sense, topological. And the other things, more or less too, right? This is just about the structure of this smooth manifold. Of course. So that's a K-theory of the C-star algebra of the fundamental group of the submanifold. Okay? And these K-theory groups are graded groups, and it's this index lives in the degree, which is just the dimension of the manifold in question. Okay, so somewhat complicated, sophisticated condition. I'm discussing a special case of that just in a second, but purely topological implies that we have no metric of scalar curvature on our manifold, on the ambient one we started with. We also won't have, by this condition, no metric of positive scalar curvature on n, but the interesting case here is that's also going up to the bigger manifold M. Good. And to sell this, let me show you that this implies a very interesting corollary, which actually was already derived by the special case which Prof. Lawson had established.
This says the index of n is non-zero inside the K-theory of pi1 of m.
N, that's all n.
So that's also n.
Yes, sorry. I should make sure that I'm writing a bit more.
Is it the reduced or the full C-star?
You can pick whichever you like. It holds for both. But so
Sorry, this kind of statement, is it independent of the spin structure?
it is not independent of the spin structure. So you have to be, but you can use whatever spin structure you like. If you, this index is not depending on the Riemannian metric. That's the important point. The spin structure, you have to have some spin structure for which this holds, and then you get the conclusion.
If there exists a spin structure.
Yeah. So in some sense, many spin structures are your friend because you can pick the most most convenient one.
Could I also just ask briefly, you said that if pi 1 is 0, then the pi 2 condition automatically implies that it's spin?
Yes.
But I didn't quite understand this because the Schick-class is in H2 with coefficients in Z mod too, right?
Right, that's true.
Can't you get something in here out of the torsion in H3 even?
No, the torsion of H1 gives you contributions to H2. So you just, yeah. So if you have a manifold where the fundamental group is trivial and the second homotopy group is trivial, then the first and second homology and cohomology with all coefficients are 0, and therefore these Stiefel-Whitney classes, which are important here, also automatically 0. Right, the corollary.
But the class is inside second cohomology.
It's in that second cohomology, yes.
But the torsion
So yeah, so let's do an aside here. So M spin admits a spin structure. So give you a site. If and only if the second Stiefel-Whitney class of M, which lives in the second cohomology of M with Z mod 2 Z coefficients, is 0. And let's say it should be oriented to start with, so that I don't have to worry about first Stiefel-Whitney class. And so just to explain the discussion, and here we have this universal coefficient theorem, which tells us that the second cohomology with these coefficients, I don't think I set this up very nicely, maps to the homomorphisms of H lower 2 into Z2 surjectively. And this would vanish because of this pi 2 condition. But there is a correction term, and this correction term is one of these acts we have seen last time, a slightly different one, but involved here is H1. And so, indeed. Okay, now, corollary of this result I pushed up now on the other hand. Let's take M, a three-dimensional manifold. And there's a good thing in this dimensions, oriented implies spin. And oriented you certainly no trouble with. And assume pi 1 of M is infinite. Nowadays we know that this is a generic case, either that, or we are in a situation of having a sphere or a quotient of a sphere by the solution of the Poincare conjecture. So that's almost always the case, right? That we have an infinite pi 1. And now we're looking for a codimension 2, which in dimension 3 means a one-dimensional submanifold. So, Manfred, do you have an idea for a one-dimensional?
I have no idea.
Sorry. Yeah. So, and we need to apply this. We need a one-dimensional submanifold of this three-dimensional manifold, which should be somehow interesting. Codimension 2, because that take a, right. So, because it's infinite, we have an interesting one-dimensional submanifold inside. We just take a circle, and by general position, you can make it a submanifold. And because it's oriented, it has trivial normal bundle automatically. So everything is satisfied. You know, just take Cassium and of the tangent bundle, yes, a normal bundle in a non-oriented could be a Möbius bundle. Right, if it's oriented, which I'm assuming. So we take S1, so embedded into M3, which represents an element infinite order in pi 1 of M3. Right, and now comes something you might believe can be done. S1 is a very simple manifold, so we can compute this index of S1 in this K-theory of the C-star algebra of the fundamental group of S1, which of course is the integers, and this K1 group for the integers, for C-star algebra of the integers can be computed. That's also the integers. And it turns out that this index is a generator. So in particular, it is non-zero.
Can it happen that the fundamental group is infinite, but every element is torsion?
Not for a compact free manifold. So I was assuming that too. Because it's finely generated. And I think you can go through the classification. Three manifold fundamental groups are sort of special, so that really cannot happen. It requires a little argument, that's true. But in dimension 3, we know that we have control of the fundamental groups. They are very special. There's this Haken decompositions, Waldhausen's results. So, okay. But now we're done because all the conditions are satisfied. We have this submanifold trivial normal bundle, injection of the pi 1, and non-trivial index. So the M, the ambient M, does not have a metric of positive scalar curvature. So with this result, we just take care of all, essentially all three manifolds. None of them can have a metric of positive scalar curvature.
Don't you need to assume that the pi 1n, the image of pi 1n is infinity index?
I made a mistake here. I have to assume as well that pi 2 of M is trivial. Right? So S1 times S2 should have been the case you should have worried about, because that is... and with this extra condition, that's, again, something to work. I just told you this is automatic. It is automatic. Okay, so the conclusion is M has no positive scalar curvature metric. And to put in this condition is also something kind of standard in three-dimensional manifolds, and essentially it just tells you M with infinite fundamental group should not be S1 times S2. That's more or less what this condition here means in practice.
Maybe this isn't quite relevant, but since we're more or less using classification anyway, is it possible to use the classification to get this in any other way?
Yes. If one knows the Oroni-Poincare conjecture or the classification of the three manifolds with finite fundamental groups, but just the full Thurston conjecture, you can deal with the positive scalar curvature question for three manifolds also in slightly different ways. You still have to probably involve the Dirac operator of some kind, an index theory, because you need an extra input why there isn't a positive scalar curvature metric. However, the amazing thing is that this really, really general result was proved way before the establishment of the Thurston conjecture by Perelman. Well, it just doesn't care about talk about the possible exotic spheres in dimension 3. I mean, the counterexamples to the Poincare conjecture, this one doesn't talk about, and now we know on top they don't exist. But it's just a different story, and I think it's very beautiful to have this possibility, which is rather, I mean, it's not the same kind of sophistication you need to prove the Thurston conjecture to prove this. It's much more direct.
So what is the index?
Right. I had the idea to, well, let's maybe do that later, so probably not. Index theory. the Dirac operator. Or rather, some people call it Atiyah-Singer operator. And let's maybe start with that. So very classically, it's done by Dirac in flat space. You would say Dirac operator, I don't think he called it Dirac operator, but, is given by, so flat space Rn, and I think it was mainly done in dimension 4 and R4. It is given by take the derivatives in the different directions, which are there, but multiply them with coefficients, and these coefficients are, I don't know, certain matrices. And I mentioned before, they're the Pauli matrices. So this is not acting on functions, it's acting on vectors of suitable rank, suitable dimension. And these Pauli matrices satisfy the Clifford relations namely, if we have two different indices, they anti-commute, the sum is 0, and if the indices are the same, the sigma I j squared should be minus the identity. So we have minus 2 times the minus 2, I guess, acting on the vectors of the appropriate dimension. And you have to make sure that the dimension is big enough to find these matrices. Right? This is, you need a representation of the Clifford algebra such that this is satisfied. 1 minus 1. Yeah, very good. I knew something. Thanks. Thanks. From this, it's very easy to see that if you square this operator, these are constant matrices, so you can compute with the differentiation, you get just the positive definite Laplacian, so minus the sum of the squares of the derivatives in different directions. Okay, that was the game, to find a differential operator, not two differential operator who is a square root of the Laplacian. Okay, so Schrödinger. And later on, Lishnerovich rediscovered this. Wondered what is happening if we do combine this with general relativity. So we have not a flat space, but a curved space-time. And he was working in local coordinates, so it would say Rn, but not with a flat metric, with a different metric. And he observed that, he proved that there is one sensible way to make a definition of the Dirac operator. So wrote everything down in local coordinates. So there is one sensible, because it has the right covariance conditions, properties, D, and it satisfies with this condition. It's not quite a square root of Laplacian. What we get is that the square of this operator is something like a Laplacian, which we like to write as nabla star nabla, so a positive definite no negative operator. But then there is a correction term, which Schrödinger in the article describes as something interesting, but physically completely irrelevant because the quantity is too small. And that is just the scalar curvature. So this was for curved space-time. So we look at Rn with a Riemann metric G. And this just means this should be an operator, right? Like the other one, it's given by pointwise multiplication with this function. So we are getting closer, right? I think I erased that, not quite. So we have to connect geometry to topology. Now we have input is geometry, right? The scalar curvature function, which is exactly what we care about, occurs here, and it's coupled to something also depending heavily on the geometry, namely this differential operator and everything. So quite where we want to be, but we're getting closer. Namely, and that is what Lignero-Wutsch then really did, and Schrödinger didn't. We were thinking about trying to globalize this. So this is something you do in kind of local coordinates, Rn, but can you globalize this on a Riemannian manifold? Okay? Now you know what it should be in local coordinates, but then you have to check that if you pass from one coordinate patch to another, things match up. Right? So globalization onto M, our closed manifold, of the construction is possible, but not always, if M admits a spin structure. I don't want to go into the details of what this is, just it's a topological condition, and it allows us to make these local constructions global by seeing that they patch up. And it gives us the differential operator D acting on the global version of vectors, but vector-valued functions become, of course, globally sections of an appropriate vector bundle. And this vector bundle is a spinor bundle. Which again comes with the spin structure. This allows you to glue these local things together to a vector bundle in a sensible way. And now we have a bit more. If the dimension of M is even, then the spinor bundle S splits into a positive part and a negative part. It's a super vector bundle. That's what super means. So I wonder whether super global university means it splits into a positive part and a negative part. I believe here in Kyoto you have just positive part throughout, and the negative part is 0. And the Dirac operator interchanges the sections of the positive part and the negative part. It's a self-adjoint operator, so these two things are adjoints of each other. And okay, so that's just a little bit of structure. And now comes the index, version 0. Okay, so properties of this Dirac operator on our compact manifolds. So D is what is called elliptic, which means it's an extremely nice differential operator. And this in turn implies that D is close to invertible. In the following sense, so after some maneuvering, D can be deformed to a bounded operator. D tilde. So I can write down what it is. It's E divided by the square root of 1 plus E squared. That's a bounded operator on L2 sections, the Hilbert space of L2 sections on the spinor bundle. So for elliptic operators, you always work with Hilbert spaces and space of this kind. And there exists, so that's the ellipticity condition, this almost invertibility. There exists another bounded operator P. Such that, well, invertibility would mean the compositions of the operators D tilde and its inverse P are equal to 1, right? So these differences would be equal to 0. Now that is not going to be true, but it's going to be small in the sense that it's lying in a very special ideal inside this algebra of all bounded operators. It's lying in the ideal of compact operators. The ideal of compact operators. And just as a reminder, the compact operators are the closure of the operators which have a finite dimension image. So having finite dimensional image is, of course, very close to being 0. In this sense, this difference is very small. It's close to being 0. Okay, that is what ellipticity gives you. Gives you this almost invertibility. And now let me set this up in this way. I like to set it up. D tilde is invertible. It is not invertible, of course, but it is invertible if you think of it as an element in the quotient algebra. Pardon? Of course, of course. This is another way to formulate this. But I'm preparing to generalization, so that's why I'm writing it that way. It's invertible in bound operators in this quotient algebra, the Calkin algebra. And now we make a tiny discretion into K-theory. I think it was also on the announcement. If you have an algebra, you can define K-groups of the algebra. And if you have an algebra of this type, which is a C-star algebra, there's only two honestly different K-groups. One of them is made of invertible elements. So we have an invertible element in this algebra, so it means we have written down an element in K1 of this algebra, just because K1 is by definition equivalence classes of invertible elements. Well, you have to pass to matrices, this is fine print, but so we get an element, a class of D, we call it a fundamental class, in K1 of the bounded operators modulo the compact operators. And now, K-theory comes with wonderful properties. So I should put those here. This is a gun. Okay, we use K-theory. So, and the basics are. So, if A is a C-star algebra, we have something called K1 of A, which is just classes of invertible elements of A. In this situation, that's a correct statement. And we have a second group, which is called K0 of A, which is classes of projectors. So projectors are things which are equal to their own square, and which we have a C-star algebra, they have a star, which are also self-adjoint. These are orthogonal projectors. Okay? And the third thing we have, if we have in the algebra A an ideal I, it should be a two-sided closed ideal. That's exactly what the compact operators are in the bounded operators. So we also have this quotient algebra, A mod I. We can write it as such a short exact sequence. Then we get a long exact K-group sequence. So the relevant portion for us is that, for instance, from K1 of A mod I, we map to, with a certain map, which we can call the index map, to K0 of the ideal. And then, because the ideal sits inside the algebra itself, we have an induced map, just taking a projector, mapping it to a projector. And similarly here, to the left. So we can apply this here, right? And we can apply this index map in this special situation, when we go to K0 of the compact operators on this Hilbert space, all Hilbert spaces are the same. So that's really just the compact operators of separable Hilbert space, which is canonically isomorphic to the integers in that case. And so we can assign to our Dirac operator, because we can make this invertible element in the Calkin algebra, we can assign to it with this machine a number which would be the baby version of the index. Here, so that is what I call the index of D living in that group. Okay. So the map really is the index. So I did actually do a slight glossing over. I should have taken here the positive part of it, because if it used the same construction to the self-rejoined operator, it would get 0. So you have to add a little nuance here. We have to work a little to use the positive part, and then of course it's also the positive part here. So just glossed over that. Anyway, this right. So in the baby situation here, the index of D plus in the integers on its identification is nothing but the dimension of the kernel of D plus minus the dimension of the kernel of D minus. Okay, but that's what you expect.
So D plus now goes between different bundles, right?
Yes, so you have to use the fact that all Hilbert spaces are the same, so you compose just with any unitary isometry between the L2 of the negative spinors and the positive spinors to have it in n-morphism. Yes. But, that doesn't hurt because the choices you make are contractible. So in the end, I should have maybe added here, if I say classes, this is really some kind of homotopy classes. So anything you can do by deformation will not change the constructions at all, which is very important. So for instance, if you have two metrics, you can always move from one metric continuously to another, and you have to go through the construction, but you will see that everything moves continuously from one situation to the other. So all I've done here is, in that sense, topological, because the Dirac operator somehow uses the metric. That's how Schrödinger was inventing it, but the index we wrote down, also this fundamental class, doesn't, just because of this important homotopy classes. So there is topology, but it's connected to geometry because of this formula, this Weizenberg Schrödinger-Lichnerowicz formula.
I'm sorry, is that true that any two metrics are all connected?
They are all connected, yes. They are not connected through metrics of positive scalar curvature, but they are connected through the space of metrics. You just take the linear path. The linear path between two metrics satisfies, that's a convex condition, being positive definite, and bilinear is a convex condition. So you can just do the most naive thing you can think of and you connect. That's when did I start? 10, right? Oh, okay. Very interesting. Right. So I can't stop this before. So now we have seen by this homotopy argument that this index of the Dirac operator defined that way is a topological invariant. It does not depend on the metric we're picking. It does depend on the spin. A priori, it could depend on the spin structure, but that's our friend. If you have several spin structures, you would even have more to play with. Unfortunately, or fortunately, it doesn't depend on the spin structure the way I defined it here, but a refined version of it can indeed. However, it's even better. There is the Atiyah-Singer index formula. Not only is this a topological invariant, you can compute it a priori without having to worry about constructing these Dirac operators and computing kernels and so on, the index of D is equal to something we call a hat genus of M, which is just some characteristic number of the tangent bundle of M, which is rather computable. So if we go to the world of smooth algebraic varieties, you have tons of ways to do calculations, and it's really pretty much all known. So for instance, for the Kummer surface, we can make this calculation. We get a number which is non-zero for this thing. Or for the complex projective plane, we get -1/8, for example. Right. And the final thing is, so the connection to geometry, if the scalar curvatures, if they are positive, and you look at the formula which was here, d squared equal nabla star nabla plus scalar curvature over 4 implies then that d squared is a strictly positive operator. And that implies that d itself, and also this thing I produced out of it, is honestly invertible. Okay? If you have a strict positivity of a real number, it means it's invertible. It has a multiplicative inverse. And that same thing works in all other C-star algebras.
You need the, also we are in compact situation, so you have a strictly lower bound.
Right. I mean, I need that this is strictly bounded below by some positive number. Right. But I'm using the compactness here. Right. And now, I guess I didn't really set this up well, but this implies that our class of the Dirac operator, which lived in K1 of bound operators modulo compact operators, actually we didn't have to mod out the compact operators, right? We could have defined the class inside K1 of the bound operators. Let's call this thing rho of D. And now this depended on the fact that we had a post-scalar curvature metric. So it a priori depends on the metric. So you see something interesting popping up. At the same time, let's observe that by the fact that we have an exact sequence, the index has to be 0 because we have a lift to the left, and if we have an exact sequence, we go 2 steps, we always go to 0. Okay, so very basic introduction with this kind of setup. And so if, for example, the Atiyah-Singer index theorem tells you that a hat is not 0, the index can never be 0, no matter what spin structure or metric. I mean, it depends on the metric anyway. And therefore, you cannot have positive scalar curvature. Right? So that's how it works. Now, we do need a spin structure for that. That's why CP2, which has a non-trivial hat genus, is not a counterexample. It just doesn't play a role here because there is no Dirac operator, because there's no spin structure. But the Kummer surface is a spin manifold. It also has non-zero hat genus. So the Kummer surface doesn't admit positive scalar curvature. Simply connect 4 manifold, which, to which this all applies. And now I'll use my last minute to explain why it sets this up in this particular way. So now we have obvious generalizations. replace compact operators as ideal inside bound operators by any other suitable. Here we have to use the specific of the situation at hand. Pair an ideal inside a C-star algebra such that we can make a Dirac operator, or out of our Dirac operator, this version of it, which is an element in the C-star algebra A, such that D tilde is invertible in A mod I, and therefore we get the index of the Dirac operator in the K-theory of I. Okay? And in addition, we expect and hope, and we make sure that positivity of the scalar curvature implies invertibility of D tilde on the nose. So we get the vanishing result of this index, and then we should also work a little bit in the direction of Atiyah-Singer to get some formulas to compute the index, and we can just you see you have a very general machine. You just have to fill with life. And I think I stole 2 minutes of you. Let me see one more, just to show you one case, which is kind of a specific case. So replace the scalars, which are the complex numbers, or maybe that's already one step, the real numbers. Now you see, along the way we work with C-star algebras which are not that simple anyway. So why not also replace the scalars by more complicated C-star algebras? And in particular, we can take the thing which was shown up before, the C-star algebra of the fundamental group of the manifold in question, which is a completion. Yeah, also n, m, yeah, x. I mean, whatever your manifold is which shows up, yeah, you're right. That's, you take the group algebra, real or complex. We do it with the real group algebra. And then you do a suitable completion of it to make a C-star algebra out of it. And there, you've just heard this before as a question, there are several ways to do it, and all of them are fine. So you can work with either, and you get suitable results there. Some might be stronger, other might be easier to compute. So,
but the group is not amenable, is it?
It's not, no. So there can be really different ones. So this is not quite well defined. There are different versions of this, but whatever you choose, you can actually work with it. That's what I'm saying. Then replace the vector bundle S by S tensor L C star I1 of M, where L C star I1 of M is a canonical flat but non-trivial bundle of C star I1 of M modules, free of rank 1 even. So they're very simple. And that just means I'm really taking serious replacing the scalars by this. Now the fibers of this are not vector spaces, but they are modules over this C-star algebra. And then you carry out the same constructions you did before. You make the Dirac operator. It's acting on sections of this, but now the scalars are replaced by this C-star algebra. So everything is modules over this C-star algebra. Every operators are.
How do you get something non-trivial? There must be some twist in the Dirac operator.
Okay, I mean, this L is not trivial. That's twisted. Canonical, non-trivial. It's a universal bundle of that kind. It's twisted as much as possible. So I could define it for you. You take the universal covering on this C pi1 of M acts. On this module, it acts by multiplication from the left. And from the right, we use the left multiplication to make this bundle. And the right multiplication is still there to produce this module structure. And that way we get, then the construction just works the same way, and all the properties we need are just more or less automatically satisfied. The local computation, because that's a flat bundle, locally it's just like crossing with this thing. And the computations are completely unchanged. Give you that everything works the same way, and we get this index of D I described before in the K-theory of, well, I should have said the compact operators on S tensored with this C-star algebra of pi1 of M, because that is then what turns out to be the role of the compact operators. But K-theory doesn't see these compact operators anyway. That's another property it has. That's why it ends up here. And this is a very strong invariant. This is sometimes computable. And there's a prediction what it should be if we take the right version. There's this Baum-Kohn conjecture, which tells us that this can be computed topologically. And indeed, you can then also compute this index in many, many cases. And you get tons of examples where you see that this is non-trivial. For example, the flat torus. The A hat genus doesn't tell us anything, but this invariant here is non-trivial with values in the K-theory of C-star of the fundamental group of the flat of the torus, which is just set to the end, so it's easy to compute. And we learn that the torus doesn't have positive scalar curvature, for example. And now, of course, I'm stopping. Let me, however, finish that the conjecture is that this index invariant here, taking values here, is kind of the strongest possible. That with that, you can see everything you can ever see with index theory about positive scalar curvature. And the codimension 2 theorem I described at the beginning is the one case where I really don't know whether it's connected at all to this. So we had this codimension 2 condition, which used the C-star algebra of the pi1 of the submanifold. So you pointed out that this was showing up. And we have also this invariant where we use the C-star algebra of pi1 of M itself and the Dirac operator on M. And the conjecture would say that the only way to obstruct positive scalar curvature on M using index theory should be via this invariant here. But we do have this codimension 2 invariant, and I have no idea how to relate the two.
Why is it codimension 2 anyway? So why can't you work with codimension K?
The proof doesn't work. I don't know whether it doesn't work. So you would need more conditions on the homotopy groups. So pi2 is because of codimension 2. We could add them. I don't know. It's an interesting.
Specific reason for. I mean,
there's no intrinsic reason. The proof doesn't work. It might well be. Actually, I'm thinking about it to generalize it to higher codimension, but we just haven't worked this out yet. Okay, and I'm 8 minutes over time, so I definitely should stop. Thanks for your attention and patience.
Thank you very much. Are there any
Do you expect the existence of positive scalar metric, scalar curvature metric to be a topological property?
Well, the question is what topological means.
It means I think if two manifolds are homeomorphic.
That is known not to be the case. So by definition, it is a question of about the smooth manifold. And it depends only on the smooth structure, because we said, given a smooth manifold, does there exist or not? So that's just by definition. Now we can take smooth manifolds, which are homeomorphic but not diffeomorphic. It was a surprise in the 60s maybe that these things exist, but they do. There are actually plenty of them. And the first examples were developed by Cavere and Milner. They're spheres in high dimensions, for example, dimension 9, which are homeomorphic to the standard sphere, but not diffeomorphic to it. And not with this invariant, but with the same machine. So using K-theory of C-star algebras, but actually, because I wrote down the R here, with exactly this case here, Hitchin was able to show that there are half of the exotic spheres of dimension 9 do not admit a metric of positive scalar curvature. Of course, a standard sphere does. So the other half does. That's the result, which again was, I think, a big surprise. So this very, very weak condition where you think you just start bending it. If you have 9 dimensions, you have so much room, and you're almost on a sphere, which is the roundest thing you can think of. It's just not diffeomorphic to it. It doesn't work. So that's really stunning what this scalar curvature question kind of displays.
And there are also examples by LeBron and Catalese of actually examples with opposite signs. Or is that
Opposite signs in which sense?
can you completely negatively curved?
So there is another, I wanted to say something about why positive scalar curvature. There is a construction by Kashtan and Warner. I think that's mainly using conformal deformations, so it's quite soft. If you give them, on a manifold of dimension 3 or higher, a function, a smooth function, which is negative at one point, also in the neighborhood of that point, of course, then they will give you a Riemannian metric which has exactly this function as its scalar curvature function. So the positivity is some kind of watershed. If you're below positivity, with negativity just somewhere, everything is possible, and in many, many ways. And then you go up, and suddenly you're above the surface, and there is air, and there is an interesting life for us humans. But I don't know whether this, I mean, there's the question whether you can have strictly negative sectional curvature is a different one from negative positive curvature. So there might be relations. And I should say that dimension 4, which is Lebrun, is definitely very different from all the rest.
Further question? If it's not a case, there's some speaker again.